Today we are going to talk about Node.js performance, and I'm going to give you 15 tips that will make your application fast, always, under any conditions for the rest of your lives. Are you ready? Yeah? Yeah? No, it's actually not going to happen, and it's quite the opposite. My presentation is about why you should not invest time in following tips and reading about tips, memorizing them, and instead this presentation tends to give you some tools and information that you can use to go ahead and create your own tips, if necessary, that are right just for your situation and for your application. So, but why is that? Why do I say that you should not invest time in memorizing tips shared by others? It's because you know that Node.js is backed up by JavaScript engines. Most of the time it's V8, but not necessarily. And if you ever followed a blog of any of these engines, for example V8, once in a while you will get a blog post that says that they have optimized the language feature that has been slow for, like, I don't know, since the existence of the engine, and now they've optimized it and now it's running fast. Which means that if you've invested time in in a tip, in implementing a tip that said that you should not use that particular function and you did nasty stuff to overcome it, you don't need it anymore, right? So, which means that those things get outdated. Those tips get outdated because folks behind JavaScript engines are working hard on improving performance here and there. Even the most nasty things like arguments array is getting optimizations once in a while. And besides that, whatever reason is making your application slow might not have a tip out there yet, or the tip might not apply to your particular application. That's why you will be stuck if you have no means to find out what's going on with your code, right? So my whole presentation can be summarized in this expression that I love very much. It says tools over practices, which we'll talk about now, the tools. So why do my applications run slow? It's amongst others because of two reasons. It's either I'm doing heavy CPU operation that blocks my event loop, and needless to say that Node.js is single-threaded, has an event loop, and every time we block the event loop, we block the whole application in case we're not working with threads, like specifically. And otherwise, we are doing some input-output operation, like working with databases, doing requests ourselves or whatsoever. In that case, again, our application gets stuck for a while. And if you look at it from API's perspective, our application is stuck, but the Node.js is kind of an idle. While the second point has quite some tools that help you figure out what's going on, like as fancy as New Relic or whatever you can implement yourself, that tracks what your application does across many applications like database and the Node.js itself, and maybe some queues and some external requests. We will today focus on CPU intensive operations and how to find them out and how to fix them. Well, actually, not how to fix them, but how to find them. How can we actually analyze CPU intensive code? Before we get into that, let's do a little bit of a recall. We all, or some of us, know that JavaScript executes in stacks, right? So we start with an entry point. The entry point itself calls a function. That function does some job and then calls the function itself. Then that function calls a function itself, and etc. When we reach the tip of the stack, we know that the stack is complete. Then we start crossing items out of the stack, which are called stack frames, and come back to the entry point. So all of that function calls together, referencing to each other, are called call stack, because they keep a reference to each other and some information about the execution queue. And one particular item in the stack frame is called a stack. In the stack trace is called stack frame, which contains information about what function needs to be executed and the environmental information like the closure variables in that function, etc. Obviously, if we want to find out how much time my particular function takes, I can go with as simple as adding date now before and after the function was executed, count the delta, and there I have it, how much time my function executed. But then again, I don't know really was that time spent doing some operation that was outside of the Node.js or inside of the Node.js. And besides that, that function can be calling other functions, like maybe 50 of them, and I will, by only calculating this particular function, will give me no information, or very little information, or I have to go everywhere and put the date now, stamps, and calculate deltas all over. And this process of finding out the performance problems is called profiling, and there are some type of profilers called instrumentation profilers that do exactly that. They insert measurement points here and there before and after the function was executed, count the delta, and there you have it, how much time your function took. But they have a significant problem. They are actually inserting code into your code, which means those items need to be also executed, which takes time. Of course, they do a good job figuring out how their own functions took, so you don't have to, and they reduce that amount from your total duration of your function, but still it's not perfect. Besides that, they insert items into your call stack, which means that, for example, V8, who is looking at your code and doing some optimization, might bail out some optimizations that it's doing, like inlining or caching or whatever it does, which means they are directly affecting the performance of our application and might not give a clear picture of what's happening in my code. So what if we instead ask the CPU what it is doing right at that moment, and use that information, which will be independent from our code? I'm sorry? It turns out we can do that, and folks have been doing that for quite a while now. And what we can do is ask the CPU, like, give me the, to simplify it, give me the name of the function that you are executing right now. And then go back to the VM and say, give me the stack that led to that function. Like, what functions were called before that function got executed and is currently being executed by the CPU. And by calculating that information, we will have two values. One says that for one particular function, is being executed right at this moment. It's in the CPU. And the other will say that there was a function that was in the stack that led to that function getting executed, right? So it's either in the stack or is currently being executed. And if we collect that information, we can do some clever aggregations here and there and come up with this beautiful chart, which is called a flame chart, which will aggregate or group common paths in our source code together with the information of how much a particular frame was either in the tip of the stack or was in the stack itself. Obviously, the functions that were mostly on the tip of the stack took the most time in our application, right? So here, for example, in this example, the blocks that are marked in red are pointing us to the places where Node.js spent the most time in. Finally, let's talk about some tools, because I said this presentation is about tools. And my two favorites, all of them are interchangeable, but my favorites are 0x, which does just that. First, asks the VM to output some profiling information. Then when it's there, does aggregations, does some statistical analysis, and generates the flame graph. I'm sorry. The next one is autocannon, which is used to just attack our server with a lot of requests to get better detail on where our application spent the most time on. Because when we have an API and it runs once, we don't have much information about what happened. But when it runs like 100 or 1,000 times, or is being called 1,000 times per second, then we know more information and we have more data to analyze. So now I'm going to demonstrate how this actually looks like. Just a little demo. Okay. Can you see my screen? I think yes, right? So I have this simple application which just creates an HTTP server, listens to the port 8000, and whenever a request is received, it does some stupid loop for like 10 million times, and then sends back the response. What I can do for this is the following. Please take a look at this command. So what I do is I say, dear 0x, please run this command for server.js. But actually first let's do the server.js. Then I say, whenever server.js is up, please run this command on it, which is the command that just attacks the server with too many requests. And I say, whenever the flame graph is ready, please just open in the browser. So here, autocannon just attacks the server. Now 0x analyzes the data, and here I have my flame graph, which directly points me to the problem spot, which is the foo function that took 99.2% of the time to execute. This was kind of obvious, but this tool can be used to analyze some non-obvious paths. Let's take a look at another example, which is where here we didn't have any dependencies from Node modules. We just depended on core HTTP module, so it was kind of a simple program. This other one is using Express just to make our flame graph a little bit more involved, let's call it so. Right. You can see that there is much more going on with this code, and you can imagine that with your average server that does much more stuff, this flame graph will be much more involved, but will still point to the problem spots in your code. And what I suggest you do is, you can see a lot of buttons in here giving some, I don't know, different types of information about your code, which I suggest you do. Because if I've included them in my presentation, it would have been like 2 hours long, at least. But there are some interesting things to go ahead and analyze for yourself. Is like, this flame graph also may include information about what your V8 engine, or any other engine is doing. What runtime functions are being executed, even the functions that are C++ functions in the V8 engine and are being called will be also there. And what's more important is this flame graph also represents whatever your V8 engine is optimizing, which means if it does some inlining or caching, then it will be in the flame graph. If it does merging of whatever optimization will be there. If you play around with different V8 flags, you will see them happening right in front of you, because the flame graphs run on the same program with different V8 flags will generate different flame graphs because different things are going on. Even the optimized and not optimized functions, which you might know that turbofan might optimize some functions for us and some functions might not be optimized and ran on ignition, then you will see them as different entities in your flame graph, which I suggest you do. Just go ahead and play around and figure out what's in the boxes. I suggest you go check out Node Clinic. Node Clinic is based on 0x, but it's much more involved and has more beautiful view UI and has some more tools that also help you figure out what's going on with your application. Gives much more information. Perf events and dtrace do the same thing that I've showed you, but they do it up until the kernel layer. So they might also, besides what's happening in your V8, they might also tell you what's happening in your operating system. They might not be the best tools for us as JS developers, but in some cases they might help, but they are quite involved to use. So if you're that curious, please go ahead and check them out. And actually, that was it for my presentation. Thank you, and we'll have Q&A later.